Yeah, okay. So looks like most people joined. So we can get started. So I should introduce myself. So my name is Jarno Vanderkolk. I'm the Senior Scientific Computing Specialist at the University of Ottawa. So that means my role is to help researchers with all their computational needs. So that could be high performance computing, or if you want to buy a server and install it in our data center, or if you need help making your code run more efficiently, like in parallel. And also, of course, these seminars that I do, well, at least monthly, sometimes more. And yeah, I'm really just here to help researchers with their research and their computational needs. And yeah, as part of that, we're going to handle machine learning today. And we're going to use the PyTorch library. So if you ever have any questions, feel free to unmute yourself and interrupt me. You can also use the chat. Sometimes I don't look at the chat for a few minutes, but I try to look at it as often as I can. Yeah, so with that, let's get started. So there are various different versions of machine learning software. Uh, TensorFlow is like a really famous one. Scikit-learn, Keras, which is now integrated with TensorFlow as far as I know. And there is PyTorch. So all these software packages can be used for machine learning, but at the core they function the same. So if you, from this course, you learn how to use PyTorch, you can use that same knowledge to use TensorFlow or Scikit-learn. It's just a different syntax, but the basic idea is the same. Um, so what is machine learning exactly? So machine learning can be a lot of different things, but ultimately it's about finding patterns in data. And it's about finding patterns in data in the same way that animals or humans would recognize things. So it's based on the brain basically. So you have all these neurons that are connected to each other. Input comes in from one side, it goes through all the neurons to the next layer, next layer, next layer, until the end where you get an output, and that output is what you want to know. And to get output that you want, you have to train your data, just like you have to train your children or your dog, for instance. And there are different types of machine learning. There is supervised learning, there is unsupervised learning, and there's reinforcement learning. So supervised learning is one of the more common ones. That's the one where you have a big data set and the data set is labeled. So you already know uh, what features correspond to what output you want. So that is the training data set. Then you train your model based on a training data set, and then you can feed it input it's never seen before. And that's where you start using your model. There's also unsupervised learning, where you have a data set that is not labeled. So you have data and you want to make distinguishments. Distinguish. You want to make draw some conclusions from it. So you want to know, for instance, how you can split the data set in half, and then the first half has a different property than the second half, and that's something that the machine learning model has found on its own. And then reinforcement learning is when you have something that behaves in a certain way. So you have like, for instance, you have like a card that has a rod balancing on it, and you want to move the card back and forth so that the rod stays balanced on it. There is no data set for that, but there is physics in play, and you know that if you turn right, then the rod will fall to the left, etc. So you don't really have a data set, but you know what you're looking for in behavior. So you can write a function that encapsulates the behavior that you want and then train a model to behave in that way. However, for this seminar, for this workshop, we'll stick to supervised learning. It's the easiest to grasp and it's also one of the more common ones that you'll see around. So you have different stages in using machine learning models. So there's the learning stage and there's the predicting stage. The learning stage is how you teach the model how to get the information from the data set that you want. And it's really slow and it's very intensive for the computer. So these models are done best with a GPU. So GPUs are really good at machine learning. That's why they're so much in demand these days. Um, you don't have to have a GPU, but it helps a lot. But for this workshop, our models are going to be very small. Our data sets are going to be very small, so we won't need a GPU. But if you get to the bigger models or the bigger data sets, then you might want to look into that. I have an example with code how to use GPU. So I'll send it out after the workshop so that you can look at it if you get to that stage. And for getting GPUs, if you don't have a GPU in your own computer, you can use Compute Canada, which is like a national consortium of clusters that have GPUs available for you for free. And then the next stage is the predicting. So once your model is trained, then you can use your trained model to put it in action. So you can load that model on your device, or you can show it new data that you actually want to examine, and that is really fast. It's like several orders of magnitude faster than the learning phase, so you don't need to have a GPU for that one. So that means you can put it in your phone, and then lots of cameras these days use machine learning. They have a trained model that can recognize images, and then that trained model they put on your phone, and then your phone app can just use it. So that's how much different there is between predicting and learning. The typical strategy for training your model is first you have to define a neural network, and that neural network has a lot of weights. I'll come back to that later, but essentially it is a lot of different neurons that have a certain weight with it, with how much they count. And your information propagates through all those neurons, but you have to set the weights correctly for it to produce the right output. So once you define the neural network, then you iterate over a data set of inputs. So those data sets can be anything you want. It can be your research data, it can be text, it can be images, it can be sound, all that sort of stuff. And then you take that input and you put it into the neural network. And it does a whole bunch of calculations. And at the end, you get a few numbers. And those numbers that you get in the end, the output, that is what you want to get from the model. So your first attempt, all the weights are just random. It does a calculation, it gets some sort of random value. And then you want to know how far that random value is from what you want it to be. So that is the loss. So that is how far the output is from being correct, basically. And then you have all these mathematical calculations that go from the input to output, but you can reverse those. And well, not exactly reverse those, but you can calculate the gradient. And if you've done math before, this is the derivative. So you can see how much, if you change the parameters a tiny bit, how much that changes the parameters. And using that gradient, you can calculate how much you should change the weights to make the output better. So you do that hundreds and hundreds of times or thousands of times. And every time you update the parameters to be a little bit better and to minimize the loss. And in the end, you'll have weights that that are exactly right for what you want to do. So you put in your inputs and you get the output that you want. And then once that is done, then your model is complete and you can use it for the prediction phase. So the last step is the simplest update you can do. So the weights, you modify them a tiny bit. So you take the learning rate, which is a number that indicates how fast your model is learning, and you multiply that with the gradient, which means the gradient is the higher the gradient, the further off you are from the correct answer. So it converges really fast down to the weights that you want. And the learning rate, if you choose that too low, then your model takes forever to train. If you choose it too high, then it might overshoot its target and it starts going way out of control. So that's a bit of a tricky part. You probably want to start low and get the output you want. And then once you get more comfortable, you can try increasing the learning rate to see if it still makes sense. For now, we won't bother too much with it. We'll just use a low learning rate, so we make sure that it always works. So this is what the network looks like. That's my mouse cursor. Yeah. So we have the input layer. So that's the data you put in. And each blue dot here, it stands for a different feature. So for instance, if you have a data set that is like data like age and salary and sex, for instance, those can all be inputs. And this input is for one data point in your data set. So age, salary, and sex. And then all those numbers, they are processed, and these lines all stands for a different weight. And they go into what's called a hidden layer. So a hidden layer is an operation. So it could be uh, multiply this line by 4, multiply this line by 5, multiply this line by 3, add it all up, and then that output goes exits that layer here. And you have many of these nodes. You can make as many as you want. And then the output of that can go into the next layer. And the output of that can go into the next layer, finally until you get the output value. And you don't have to have one output value, you can have multiple as well. For instance, for this model, you could have, I forget what I said, like age and salary, and then it goes through the model, and then this could be like if you're eligible for a loan or not, for instance. And yeah, that is what a neural network looks like. And these layers, there are many different types of them. The simplest one is the one where I said that you just multiply it by a number and add all the inputs together. But there are all these different ones as log, there's very complex functions. We'll just stick to the basic ones to get a model up and running, and then you can take it from there yourself, just to get the idea of all this is. So now we're going to get set up. So I have a website, or not really a website, I have a cluster that we can use for training. So if you go to this link here, so ML workshop, so machine learning, mlworkshop.c3.ca. And if you go there, you'll get a login page. I'll just click on that. And I'll put that in the chat. So you can log in there. And I'm going to give everybody a username. So let's see, how many people do we have? So we have 20 people. And I'm just going to put it in the chat. So like that. There's probably a way to automate this, but I didn't have time to do that. Christopher.
Yeah, no, sorry. And regarding the password, which is the password?
Yeah, the password is ML for everyone, and
Oh,
it's capital sensitive.
okay. Thank you very much.
Let's see, I was saying code. Oops, I misspelled that one. Well, 15, 16, 17, 18. Oh, OTP, you can just ignore that. You can leave that blank. The password is ML for everyone. It's on the screen, Gotham. Okay, that should be everyone. Did I miss anybody for giving them a username?
Yeah, no, sorry. I set for 1 hour instead of 2 hours.
Oh,
You think this will be a problem? Because I
um, it
cannot
might
use.
time out, but that's okay. You can just restart then if that happens.
Okay.
Okay, so I am going to be user 01. Yeah, so then you get to this screen here and you get to set the time. So this workshop is 2 hours, so you can set that to 2 hours. And then you press start and then you wait. So everybody should get a screen like this in this Jupyter Lab notebook. It tells me that user 06 is already running. Oh, okay. I'm guessing somebody already took that username. Maybe I just typed it twice. The address to go. Yes, that is. How do I get that? So this is the address to go. So I'll just type it in there. mlworkshop.c3.ca. Oops. Yeah, so is everybody still trying to get, or is anybody still trying to get here? Just let me know and you can unmute or you can type in the chat if you have trouble. Okay. So the next thing is to start a new Python notebook. So under the notebook heading, you have Python 3.7, and you can click on that. Ah, good to know, Andre. So if you click on that, it opens a new notebook like this.
I have a question, Jarno.
Yeah.
How do we start this like on a Mac from scratch? Do we have to go and download Python 3.7 or download PyTorch? Can you just say a few words about
Yeah, sure.
that?
So yeah, generally you would download Python to your own MacBook.
So that's a freeware. We just Google Python and
Yeah, exactly. Um, and then once you have installed Python, you can install Torch on top of that. So depending on how you install Python, like you use pip or use conda, if you just download Python, you'll have pip, and then you can use that to install the Torch package in Python. Um, but maybe easier is to use the Jupyter interface that Compute Canada offers. So if you have a Compute Canada account, then you can log into their Jupyter environment, and then it's maybe easier to use. But then you have to wait for resource to be available. So the best way is to install it on your own computer until your models grow too large.
so if I'm going to be teaching some of this with students, it's better to just have them all download it themselves rather than give them all an account on Compute Canada and have to wait for their turn to compute.
Um, that's a good question. Like this way with the web interface, nobody needs to install anything. So that's really ideal for teaching. But if you want to work more on it outside of the teaching hours, then it's easier to install it locally. So it's a bit of a
Right.
trade-off.
Okay.
But
Thanks.
we can talk about this more afterwards if you want. Oh, I see some people in the chat also recommend installing Anaconda. Yeah, so Anaconda is a really good one. It makes it really easy to install Python. But wouldn't you access environment through a browser, Mac, Unix, or Windows? Yeah, I mean, it depends. So you can install a Jupyter notebook locally, and then you would still access through the browser. Or you can install Jupyter on a server, and then everybody can just go to that server. Let's see. From experience, if you want to dabble with this one on your own, I think UserCan is the way to go. It includes Python and a bunch of standard packages. Yeah, I agree. Anaconda is a really user-friendly way of installing Python. There we go.
And that's good for Macs?
Yeah, it works for Macs, Linux, and Windows. I think you can
Perfect.
even install it on your phone if you want. Okay, so we can try loading Python. So you have this interface, and this is where you can type any Python command that you want. So you can do 1+1. But we're going to type import torch, and you have to press Shift Enter for it to load. So if you type import torch, it will load the torch library in Python. It takes a few seconds because torch is quite big. And as long as you have like a little star in front of it, that means it's still loading. Oh, this was faster this morning. Oh, increase notebook screen size. Yes. Here we go. Sure. This is taking a while. So this cluster is set up that everybody gets their own machine, basically. So I'm not sure why this is taking so long. Should be able to handle it easily. Oh, there we go. So yeah, that took a while to load. But you can see that the star changed to 2. And that means that the torch library is now loaded. So I'm guessing it probably takes a while for you as well. Yeah, we're all doing the same thing at the same time, but I was hoping that since everybody has their own machine, that shouldn't matter. Anyway, assuming that you loaded the library, now you can use the torch functions. So that's what I have in the next slide. So the way it works with PyTorch is they use what's called the tensors for input and output. And they're like arrays, but they have additional functionality that helps with machine learning. And one of the biggest ones of that is calculating the gradient that I mentioned earlier on the fly. So there are a bunch of commands that you can use to create these tensors. So I put up a few here. So if I go to my notebook, so torch.empty, that creates an empty tensor. So here I say the size. And then I get a tensor with 12 elements. And they're all just random numbers because I said it could be empty. So it doesn't fill in the data and it just takes whatever bits were available when I created the array. I can also make zeros. So oh, that's not what I meant. So that gives me an array with 2 zeros. And I can also get it 2-dimensional. So 2 by 2 or 3-dimensional, 2 by 2 by 3, etc. You can also fill it with ones. So let's have 13 ones. And you can have random numbers. Random numbers. Those are all random numbers. Yeah, sorry, you have to press Shift Enter to execute. If you just do Enter, it just makes more lines. So it's Shift Enter. And you can get a range of numbers as well, from 0 to 10. And you can specify the step size if you want. So there's lots of different ways to make these tensors. And these tensors you always need in PyTorch. That's what goes into your model, and that's what comes out of your model. And it also has provisions for working with the GPU. We won't do that in this workshop, but it's also a very powerful feature of these storage tensors. So is everybody successful with that?
I'm
Silence is
okay.
good.
It's working.
Oh, sorry.
It's working for me. Very good.
Oh, I see somebody still importing Torch. Huh. Didn't expect that to take that long. Yeah, I'm not entirely sure what to do about that. It will finish eventually. I'll just go to a bit of the theory section, and then hopefully Torch will have loaded by then. Okay, so what did the last command do? So that's the A range. So that gives you a range of numbers. So it goes from 0 to 10 with steps of 0.3. So you can see F0, 0.3, 0.6, 0.9, etc. It goes all the way up to 9.9. because 10 doesn't, it's not a multiple. You're welcome. Okay, so to build a model, we need to define the layers, and we need to define a loss function, and we need to define an optimizer. So the layers are the simple calculations that make up your entire network. The loss function is the difference between what you want the model to predict and what it actually predicts. And the optimizer is the function that tries to minimize that loss. So it does that through a method called gradient descent. I'll get back to that. So there are many, many different layers, like there's hundreds of them. PyTorch has like documentation on their website, and there's very many of them. So I'll just open that. So you have convolution layers, pooling layers, spanning layers, you have activations, recurrent layers, all these things. I don't know what most of them do. Linear layers is by far the easiest, and that's the one we'll be using. But as you can see, there are many, many of them. Even for the linear layers, you have multiple different ones. And they all have these different transformation that they do. So y is the output of the layer, x is the input of the layer, and a to the power t is the transpose of the weights. So you're multiplying the weights with the input, and then you add a bias, and that gives you the output. So this A matrix, that contains the weights that you want to train for. So that is what we're going to stick with. And the A's here are of what we are going to train. We're just going to ignore any of the other layers and just stick with linear. And we start with the simplest network of them all, a single node linear layer. So here on the right is our graph that we are going to use for a network. We have one input value, which is x. We have one linear layer node, and that produces one output y. So this is of the form y equals wx plus b, because wx plus b, that's what this matrix does, this layer does. It just multiplies x by some weight and adds the bias. So this makes it perfect for fitting data to a function like y equals mx plus b. So we're going to do what's called a linear regression. We're going to use machine learning to fit a line to a curve. And if you know anything about fitting, fitting is about minimizing the difference between our fitted function and the actual values. So that's the difference between y, which is the output that we want. So that's the fitted function, and y prime, which is the prediction. And then we need to minimize the loss. So you need to some way to compare like the guess for the network with what you want. And again, there's many different methods. So if I click on this link here, these are all loss functions that are built into PyTorch. Let's see. So the goal is to try to minimize the learning error. Yeah, pretty much. You're trying to minimize the difference between what you want and what you need. Sorry, the difference between what you want and what you have. Yeah, so there's all these different loss functions, like L1 loss, MSE is mean square error, there's cross entropy, there's a whole bunch of other ones that I don't know what they are either. Just that they are loss functions that you want to use in specific cases. And as you can see, there's many, many of them. But we'll stick to the simplest one, which is the mean square error. It's this one. And the formula for that is this thing here. You may already have you may have already seen this one. It's a pretty common one. So you have your value that your model predicts and the actual value, and you take the difference between those functions and you square them for every node value in your network, and then you sum it all up, and then you take the average of that. So it's the mean square error, and it's a very common one. It works most of the time. So if you minimize that, if y equals exactly to y prime, then this becomes 0 and your error is 0. So you're trying to minimize this. And the minimizing is done by the optimizer. And the optimizer uses some form of gradient descent. So gradient descent means if this is a plot of your mean square error as a function of y prime, then there the minimum is where your mean square error is the lowest. So that is going to be the best that your model can do. So you want to go from here to here. And the way to do that is if you are on this plot and you calculate the derivative for the gradient, then you know in which direction you need to walk to go down. So here the gradient is about 1, I guess. So you want to take a step into the negative of 1. Sorry. You want to take a step into the negative. So you take one step, -1, that gets you on the plot here. And then you do the same thing again. The derivative is still -1, sorry, +1. And take a step in here, and take a step in here, a step in here. And then from here, you can, if your learning rate is too high, you can end up here. But that's okay, because then your derivative is now going down, so -1. So that means you have to take a step in the other direction. So it slowly converges onto this point here. So yeah, and PyTorch takes care of the calculation of the gradient derivative for you. So you don't have to worry about that. It's all being done for you. But this is how it works behind the scene. And here we only have one value for y prime because we only have one input value in one dimension. But you can imagine as you get more and more inputs, you get a 2D plot and then a 3D plot and a 4D plot and a 5D plot. So you can't really imagine the path that the gradient has to take, but the math stays the same. As long as you walk in the opposite direction of the gradient, then you go to the lowest point. And there are various ways of doing this, because for instance, if you're over here, then the gradient points to the right, and that means that you go to maybe a minimum that is not the best minimum. So there's different ways of dealing with that. But we'll just stick to the simplest case and assume this. And in Python, in PyTorch, this is called the stochastic gradient descent. It's the gradient descent, but it only takes a fraction of the information, which makes it a lot faster, but it also makes it more erratic. But if it's more erratic, it means it also explores the whole ND space. So when you have all that, you can put it together to a machine learning algorithm that minimizes the mean square error. And that's what I have on the right. So here on the top is my epoch, and epoch stands for a learning iteration. So you iterate over the model many, many times to try to minimize the mean square error. And the red line I have here, that's my model. So that is the function y equals mx plus b that I mentioned in the beginning. So it's the function for a linear line. And the blue things are the data points that are the input for my model. And the y value is what I want them to be. So here I'm teaching my model that -1 corresponds to -2. I'm teaching it that 2 corresponds to 4. And that 3 corresponds to, well, not exactly 6, but just a bit under it because I added some noise. And as the model gets trained, you can see that the red line gets closer and closer to the points that I'm trying to teach my model about. So that's pretty neat. And now we're going to try to do that ourselves. So there is a notebook in your home directory already called linear regression exercise. So if I go back to my Jupyter lab, you should have something like this on the left. And there's a folder called ML Workshop. If you double click on that, there is a linear regression exercise. And you can double click on that and it will open it in your Jupyter notebook. And then there's a bunch of libraries that we want to import. So we click on that cell and do Shift Enter. And it's going to do the import again. And I hope it doesn't take as long now as it did last time, because that's kind of annoying. Let's see, a question. How do we determine the optimal number of hidden layers? Can we let the model decide how many hidden layers it wants to create? Yeah, so that's really the dark art of machine learning. There is no good, uh, there's no real good answer saying if I want to learn this, I have to use this many hidden layers and this many nodes per layer. You basically just try something and see how it works, and then you try to tweak it. So you add more layers, or you remove more layers, or you add more nodes in the layers. You try different layers. And actually, you can use machine learning to find the best machine learning model for your uh, for your data set. So you can actually train a machine learning algorithm to train a machine learning algorithm to predict your data. But then it gets kind of complicated. And also, the more layers you add, the more accurate your model is going to be. But also, the longer it takes to calculate things. Because if your model gets too big, it just takes forever to train. And you don't really want that. Okay, so I hope everybody was able to open linear regression and execute the first cell with Shift Enter. It should change from a star to a 1 like I have here. So I'll give it a few minutes because I know people have trouble with this. Let's see, I got MATLAB is building the font cache. This may take a moment. Yeah, that's correct. I got that too. So the first time you import matplotlib, for the first time it builds the font cache. It should be fairly quick though. Can you please share the slides after? Yeah, I will send the slides out to everybody, including all the code examples that I have here. Oh, I also forgot to mention that I am recording. I should have done that at the beginning. So I am recording this whole session. If you don't want to be recorded, just let me know and I'll make sure it disappears from the recording. Okay, so we've loaded all the libraries. So we've loaded Torch, which is the machine learning one. Matplotlib is something we'll use for plotting and the same as Seaborn. So that lets us plot stuff, which is nice. So here we have our linear model again. So we have one input, one layer, and one output. So that is the linear node that I mentioned before. So y equals ax plus b. So we want some inputs. So we can create a range from -3 to 3 with steps of 0.1. And that's going to be the input. Let's make it bigger a bit. There we go. So that is the A range that we mentioned before. So we go from -3 to 3 with steps of 0.1 and then Shift Enter. And that is now stored in the variable x. And then we can use that data to create linear data. So I want to create some sample output just so I can teach my algorithm about it. So I'm going to try 2x minus 0.3. So it's 2 times x minus 0.3. Wait, like that, I guess. Did I do that right? Yeah, okay. So f equals 2 times x minus 0.3. So that is going to be my simulated output. So I'm going to train my data for this input x, and I wanted to output f. Well, not exactly f, I also want to add some noise. So the way to do that is f plus wait, how did I do that again? Random numbers. How many do I have? The size of f. Yep. Yeah. Okay. There's too many languages going on. Actually, that was too much. I just want a little bit of noise. So what I did here is I took my f values, which is 2 times x minus 0.3, and I add noise. So my rand function, it creates a tensor with full of noise. Back up a bit. Yeah, like that. Oh, too fast. Sorry, yes. Yeah, by the way, if you never used Python, Jupyter notebooks before, with plus you can create new cells. So if I click on this cell and I click on plus, I get a new cell. And then I can put in x to get my values of x, for instance. So shift enter. It shows me the tensor that goes from -3 with steps of 0.1 all the way to, well, not 3 including, but yeah, close enough. And then I create the linear data 2 times x minus 0.3. So I'll just remove that one again so it can fit more on the screen. And then I want to add some noise to the input data. And let's see. My version didn't have the separate code blocks with the line that prints f, but you can add a new code block with the little plus sign in the top left of the window. Yeah, exactly. So that's what I've been doing here. So you select a cell and you click on plus and you get an empty cell below it that you can enter code in. So I added too much noise here. You can see the output is now very noisy. So I want to add just a little bit noise. So 0.05 for instance. And then my y will be pretty close to what it's supposed to be. So it goes from -6-ish to -6.3 to -6.1, 5.8. So it's trying to do the same as f, just it adds a bit noise, and that's just to make it a bit interesting. So did everybody get the y? Because that's going to be the output that we want to train for. Okay, I see yeses and thumbs up. Good. So this type of code, it's for plotting. So you can just execute it as is, and it should plot the y data, and the red line is uh, the line that we're trying to get. So I can go through this code a bit. So pandas is a really nice Python library that lets you manipulate data very easily and load it. So you create a data frame based on the x, y, and f. So x is the -3 to 3 that I created. Y is the data that I made. So that is y here. And f is the pure function that I had before without the noise added. And then I use Seaborn, which is called SNS here, to plot x versus y and x versus f. So that's what it's showing here. So yeah, the blue points are the data we're training for, and the red line is what we want to get. And then we're going to actually create a model. So what I have here is the base structure. So we create a new class in Python, and we can call it anything we like. I call it line fit model here. And it builds on top of NN module. So NN is part of Torch. And then we have our init function. That's where you define the layers. And then we have the forward function, which is where you connect the layers. So if we scroll up a bit, this is our graph. So we have one layer that we're going to define, which is this one here, which is the linear layer, and it's going to have one node. So that's what goes in our init function. And then we have the calculation, so that is going from here to here, getting that. So our forward function should result in y prime. So what we're going to say is take the linear layer, take x, and output y. So that's here. Oh, I see Palmer, has like a lot of noise. Yeah, Caroline is probably right that you left your noise to 1 instead of 0.05. I changed that later. So if I scroll up a bit, it's I added 0.05 later on. It might still work actually. I don't know. It's pretty good at fitting, so it will probably work just as well. Yes, okay, so the model. So we're going to define our layers here. We can call it anything we want. I'm going to just call it FC1. And then we're going to get that from the layers, sorry, from the PyTorch. So NN is what I imported before. Just scroll up a bit.
Sorry, Arno. Why self?
Sorry?
Why do you call it a self dot something? Why self?
Why self? It's because it's inside of a class. So it's part of the Python language. So if I want it to be local to that class only, I use self.fc1.
Nice, thanks.
Okay. So the NN, that is something we imported from Torch. So those are our neural network functions. And I'm going to do the linear layer. So dot linear. And then I need to give it two inputs. The first input is a number that tells me how many data points it can expect. So then we go back to our model. We have one input value that goes to the function and it gives me one output value. So that's what we want. So we want one input value and then one output value. So now we've defined the layer. It takes one input value and it produces one output value. And it's a layer that has what's called um, that has the weights in it that you want to teach a model about. And then we need to connect them. So we're going to use that layer that we just created. So x here, the second argument for our forward function, that's input. And we're just going to override that. So we call our layer fc1 and we put in x. And maybe this is a bit confusing. We can just do it like that. Doesn't matter. So x is what's going to be put into our model. And our model is being evaluated through the forward function. So we take our linear layer, we put in our one input, we get our one output out, and that's obviously that's what we return. So that's our whole model. And then we, yeah, sorry. And then we instantiate it. So model equals our line fit model with the brackets. So if we run that, we should not get any errors. And now our model is defined. And you can put stuff in there. But like I mentioned, PyTorch wants tensors, not just numbers. So here we create a tensor that has only one data point in it, which contains 2. So if you evaluate that, we get minus 0.1422. And you probably get something else. This is like totally random because our model has not been trained yet. Like ideally, we would want, let's see, let's make another cell. So our model was 2 times x plus 0.3, I think. What did I take? Oh, minus 0.3. Sorry. So if you were to put in 2 in our model, we should have gotten 3.7, but we get minus 0.422. It's because our model is totally not trained at all. So did everybody manage to define this model without any errors? You should get the chat back up there. Or if you have any questions about it, of course. Note that the commands are case sensitive. You have to use linear with a capital L, not linear. Yeah, that's correct. So Python is a case sensitive language. So you have to be very precise to have a capital L there. Yeah, and these functions are defined in the Python documentation that I had open earlier. So yeah, and then linear. So that's the one we're using with the capital L.
What's the definition of a module? Why do we have to say nn.module? Is that a Python thing or?
It's a torch thing. So the torch library, a package, it defines a class called module. And module is what you use to build your own models on top of. So all the helper functions are in module, and you just define some functions on top of that. But all of the work is being done by this function of torch. Okay, so then we have the criterion. So that's, in our case, it's going to be the mean square error. And we want to, well, we want to use that one. So if you remember from, let's see, the loss functions, we had MSE loss. So that's the mean square error that we're going to use. So we put that in here, mean square error loss. And you don't have to give it any arguments, you just define it like that. And then we have the optimizer. So for that, we're going to use the stochastic gradient descent, which is like a fast version of the normal gradient descent. And that also is very common in the machine learning. It's one of the easiest ones and it works most of the time. So that one is defined in Torch. In the sub, not sure what to call it, sub package or something. Anyway, it's defined in here. And then it's a stochastic gradient descent, so SGD. And we want to put in our model parameters. So this function works on our model, and it calls a subfunction parameters, which contains all the weights. And that's something that nn.module that our class is based on does for us. And then finally, we have to specify the learning rate, so LR. And we can take that something small like 0.01. And then shift enter. So now we have all the components that we need. We have the model, we have the loss function, and we have the optimizer. And those are the three things that we need to have. Yeah, so did that work for everyone?
Can you just go back a bit to the beginning? I missed one of the random torch setting, torch rand.
This one?
Yeah. Okay, thank you.
Sure. Okay, I can just put it in the chat, I guess.
And put the other one for Panda as well, please.
Oh yeah, sure. Well, the pandas one is already in your notebook, so you don't have to change anything there. You can just execute it.
Okay, thank you.
And I'll just put this model thing in the chat too. There you go. Okay, so then we get to our training stage. So here are the epochs. That is the iterations that you use to train your model. And the more iterations you use, the better your model will become. Sorry, just get some. Yeah, so the more iterations you use, the better your model becomes. So we're going to predict our y, and the prediction is being done by our model. So we remove the dots, and just like we had before here, we put in some value and calculate what the model predicts. So we use model and then our input, which is x, and it's capital X. So that's the x that we used in the beginning. And that's the one that goes from -3 to 3 with steps of 0.1. So our model takes our input data, which is that series of numbers, and the output is going to be another series of models, which our current model is predicting. So the first time it is going to be really bad. So that's the random value that we got before, like -0.41422 for the value 2. So it's all going to be random numbers like that. And then we're going to compute the loss. So we had defined our loss function here, criterion. So that's our loss function. So criterion. And we're going to look at the difference between our predicted y, which we just defined here, and the actual y that we're training for. So that's the y we defined earlier, which is our 2 times x minus 0.3 plus the noise. So here we're calculating how far off our prediction is from the actual data. And then we have these steps here, and that's the actual training of the model. So this is something the optimizer.0crat is something you always need to do. It has to do with the internal workings of Torch. Basically, you reset all the calculations that were done in previous iterations. You set them back to 0. So this is something that you always have to do. And then last out backwards, that is the step that actually calculates the gradients that we mentioned earlier. So it calculates the gradient of the mean square error with respect to our input data. And it calculates all the gradients. And then it does the optimizer step. So it does a stochastic gradient descent with the model parameters that we have and the learning range of 0.1. So once you have all that, we can execute it. What did I do wrong? Um, I don't see the error. So there's an error in my model. cannot be multiplied. So it's saying that the model is wrong. I'm just going to look at my cheat sheet here. Did I type something wrong? This is my linear layer from 1 to 1. This is my calculation where I'm inputting the layers. That's the same as what I have. So I'm not sure what's wrong here. In my notes I have this as X, but that shouldn't matter. So let's just try that again. That's that, that's that. Okay. Layers are connected here. And the weights are not the same. Okay, we're at the halfway point anyway, so I'm going to call for a 10-minute break while I figure this one out, because I don't see right now what is wrong. So we'll be back at 11:18, and then we'll then we'll continue from there. So unless you figure out what is wrong, then you can put it in the chat. Okay, I'll see you in 10 minutes at 11:18. So hello again. So I figured out what the problem was. It's a really sneaky problem, and I remember it got me stumped a lot in the beginning as well when I was trying to figure it all out. So the issue is with the input data. So let me just share my screen again. If I scroll all the way up, I create a range from -3 to 3 with steps of 0.1. So the way that looked is it is one array with all my values. But the way that PyTorch sees this, it sees it as one input with 60 features instead of 60 features with one input. So instead of having an array like this, we need to have one element per data point instead of one data point with 60 elements. So the way to do that is with a function in PyTorch called view. And view lets you manipulate the shape of the data. So instead of having 1 by 60, we want it to be 60 by 1. But I don't like to remember that this has 60 elements, so instead we use -1, comma 1. So the -1 means that you tell PyTorch like you figure it out. So when I do that and I look at my tensor, you can see it changed. So now there's one element. So there's 60 inputs, 60 points with one input, and that's the way we need it. So that's what was going wrong earlier because we defined a layer that took one input and made one output. And instead we gave it 60 inputs and it did not like that. So you need to change the first one where you create the A range. You have to add view -1, comma 1. So I'll just put that in the chat so I can. Oh, I see a question. Why not use a transpose command? Yeah, that works too, except that these tensors, they can be many dimensions. So the view is more versatile than that. It can transpose in any direction that you want. Yeah, I'll just put that in the chat there. There we go. And I'll get rid of that because it's too big. So now we've defined our x. We need to execute this one again. We need to execute that one again. And if you look at the y now, you can see that it also changed. And let me just double check that I did that right. Looks right. Okay. So this should still be. What's going on here? I made an error here. Exact size. That's the same error as I had before. Yeah, that's more like it. So you need to use x.size, which I should also put in the chat. Yeah, the error is now in pandas, exactly. That's because because of this one. Wait, did I copy the right thing? Yeah. So because I did the x wrong, I added the noise wrong as well. So you should use the size of x instead of ln of x. Because I was adding an array of random noise to every f basically. And that just made the y completely weird. The y should look like this. So the same as x, like one element per input. And then this should work. Yeah, okay. So sorry about that. I hope everybody can get the graph again. So it needs to be view minus 1, 1 for the x, and the random numbers needs to be on x size instead of ln. I should have followed my notes more closely instead of thinking that I knew what I was doing. Okay, so then our model, let's just run it again. Criterion, optimizer, and then we get to the training. So now it should work. There we go. So I'm printing the loss here. So you don't have to worry too much about the format here. But epoch, that's the number of the iteration. And then loss dot item, it gets the value of the mean square error. So our loss, we define that as the mean square error. Sorry, loss was the criterion, and the criterion is the mean square error. So loss contains the mean square error, which I'm plotting here as a function of the iteration. So you can see that the mean square error decreases, 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 all the way to, I think I gave it 400 iterations, so that goes on for a while. Yep. And then we can plot the results. So that's the code as is, you can just execute it. And now you should have a line that goes through the data. So goodbye, Andre. This will all be recorded and I'll send you the slides too for the next part. So is anybody running into horrible errors like I did before? Okay, so now going to our next adventure. Let's see, where are my slides? So yeah, there was a question before about how do we know what layers to take and how many. Oh, let's see, I see a question. Can get better model fit using machine learning than using algorithms, let's say in R? No, actually. So what you just did, it's actually very, very close to how the fitting functions already work in R, for example. So in R, you do like least chi-square or something like that. So you're already taking the mean square error that you're trying to minimize by taking the derivatives of the whole thing, and then you can actually just, well, So R is maybe even a bit better because it does it in one iteration. For the machine learning, you have to do many more iterations, so it takes longer than R would do it. But it was just the simplest model that I could possibly think of. Okay. So yeah. So how do you know which layers to use and which loss function to use? So like I said before, it's a bit of a dark art, but I found this table from when we still had access to LinkedIn Learning. Unfortunately, that contract expired, so we don't have it anymore. But this is, um, yeah, this is a good rule of thumb of what functions to use for which problems. So binary classification is when you try to classify something as true or false, or male or female, or 0, 1, or whatever. And there's all these other ones like multi-class single label classifications where you have multiple inputs and you want to create a single label for that. And that label can be multiple things, like it could be a color, for instance. And then there's a multi-label classification where you get multiple labels for your data. Regression to arbitrary values, that's what we just did. So we don't have any special layers, we just use linear layers. And we use the mean square error for our loss. And then there's, actually, I'm not entirely sure what this one is, regression to values between 0 and 1. Anyway, um, so that we're going to use that now for another example. And we're running a bit late, so I hope we can get most of this done before noon. And we're going to extract the sex from the name. So, you know, when you have a name, most people can immediately tell if that person is going to be male or female, just based on a name. But that's really hard to encapsulate in rules. You can't just say, oh, if it ends in this letter, then it's male, and if it ends in that letter, it's female. Well, I mean, you could, but it's going to be extremely complicated process. So we're going to instead train a model that is going to recognize the sex based on a name. And to find that, we need to figure out a strategy. So we go back to the table again. So yeah, which one of these would be the best fit for what we're trying to do? And you can unmute yourself or type in the chat. So we're trying to find the sex of a name. So we want to know if a name corresponds to a male or a female. So I see binary classification, and yeah, that's exactly right. So we want to find male or female. So binary classification. So that means that we're going to use the sigmoid layer, and I haven't talked about yet, but that's a special layer that um, it activates if you go above a certain value. So that's very similar to how neurons in the brains work. Like you get to a certain value, and then when you reach that value, then it activates and it sends a strong signal. So the sigmoid function, it emulates that. Yeah, that's the one. And so we now have an idea of what we want to do, and then we need to get some data. Ontario has a really nice website called data.ontario.ca, and they have lots of data sets on there. And since I'm interested in names, I found a data set that shows you the baby name frequency per year from 1917 to 2018. And if you took my previous Python or R workshops, you may recognize this data set. It shows you for every year how many babies were born with a certain name. But the thing we're interested in right now is what name corresponds to what sex. So that dataset, it has 8,823 unique names and the sex associated with them. Unfortunately, it's biased data because these are all the babies that are born in Ontario. So it's going to be mostly Western names. Not all of them, of course, but probably the majority. So that's also a big issue with machine learning. It's only as good as the data you put in it. And that's why you hear all these stories about machine learning algorithms discriminating against men and women or people of color and all that stuff. One famous example actually is with Zoom. So Zoom has a lot of trouble finding the face for people that are not white. So if you have something white in the background, it will think that is your head instead of the person sitting right in front of you. And that's because they use data sets of mostly white people. But for here, it's just for demo purposes. So we're just going to go with this one. So our input data are names, and there are two issues with that. So our network, it has a fixed number of inputs. So if we have a name with 5 letters, you have well, 5 letters, and you have a name with 4 letters. But the layer that we want to calculate our stuff with, it's fixed. So that's a problem. And the other problem is our data are letters. And machine learning, it requires numerical input data. So you don't know, mm, yeah, how do you translate letters to numbers? So for the fixed length solution, one solution is to pad with spaces. So if I use, let's see, 8 inputs and I have 5 letters in my name, I just add spaces to the end. But the downside of that is that the ending moves to different positions. And what I mean by that is that for a 5 letter name, the last letter will be in position 5. But for a 4 letter name, the last letter will be in position 4. So that's confusing for the machine learning algorithm because it doesn't have a concept of last. It just sees letter or spaces. One thing you could do is pad at the beginning, but then you just shift the problem and you make the algorithm focus on the ending instead of the beginning. I mean, you can also split it in the middle. The downside of that is that it just kind of looks weird. It might work. I haven't actually tried this one. Um, but for just getting a fixed length, we're going to try just the first one, where we just pad with spaces at the end. And then the next problem is that letters are not numbers. So, like, how would you get your name to correspond to a number? So my name, would it like be 1 or 3.1.4.5? Or would it be a series of numbers like 1, 2, 3, 4? So you have to find something to convert letters into numbers. One thing you can do is you can take like the alphabet and then say A equals 1, B equals 2, C equals 3. You could do that, but it makes things murky when, like for instance, what does 1.2 mean? Like a little bit of A and a little bit of B. And why would A be closer to B than to E? Like E is a consonant vowel. Yes, vowel. Sorry. So A would be closer maybe to E because it's also a vowel. But yeah, that's all kinds of weird. So the way around that is called one-hot factors. So instead of associating one number per letter, you associate 26 numbers per letter, and you set it to 1 for that specific letter. So instead of saying A equals 1, we say A equals the factor 1, 0, 0, 0, 0, 0, 0, B equals the factor 0, 1, 0, 0, 0, 0, etc. So now all the letters have the same all distance in vector space to each other. So that just makes more sense. And this is used a lot in natural language processing, which is kind of what we're doing. So we're going to try that now. And if you want to open the notebook called classification exercise, so we go back to, not there. Where is my browser? There. I can close that one. And we're going to open classification exercise. And then we have to import again. So Shift Enter. And while that is running, So this is something I already said. So these are the links to the actual data set that I used. And I already processed the data for you, because if you look at the raw data, it's just name and then the number, sorry, year, name, and then the number of babies born. And I just want the name, so I created a data set called data.csv, and it only contains names and the gender. So we can read that. So I'm reading that with pandas. And then the head command shows me the first 10 entries. So here are the first 10 entries in that file. You can see Adam is male, Aden is male, Adja is female, etc. So that is our input data. And then Pandas comes with a nice feature where it can split the data. So the way it works with teaching a model how to interpret things is that you want to keep some of the data separate. You take 90% of the data, you use that to train your model, and then you use the 10 remaining percent to test your model, just to see if it actually works. Because you need to test your model to see if it actually makes any sense at all. So what this function here does, it takes 90% of the names and put that in the variable name sample. And it also randomizes the order when you do that. So these are names that are in our input data. And then this code here, it's a bit complicated, but it is code that takes a sample. It takes the difference between the names and the name sample. So these are all the names that are not in our training data set. So these didn't make it. And these are the names that we're going to use for actually testing our model. Yeah, so then I said we need to have a fixed length. And then this is all code that it gets you the maximum length of the name. So in our data set, our longest name is 15 characters long. So we want our inputs to be for 15 letters, and all the names that are shorter than 15 letters, we just pad with spaces. Okay. So then we need to find our alphabet. So our alphabet is not just A to Z. There's also all these accents. So when I run this code, which counts the number of letters, unique letters, I can see there's 41 characters in there. I can actually show you what it is. Sorted letters. You can see we have the hyphen and all these extra symbols. Not even sure what this symbol is here. I don't think I've ever seen that in a name. But yeah, so there's 41 characters. So that means we have names that can be 15 letters at most and 41 characters. So since we're using the one hot factors, which means we have 41 numbers per letter. So we have 15 times 41 is 615 input values. So any name can be represented by 615 numbers. So that's quite a lot already. And then we create some functions. Not sure why this one is here twice. Oh, I know why it is here twice. We only run the first one. So this function takes the name and it converts it into a tensor. So only run the first one, ignore the second one for now. So this one translates our vectors. And there's a function here, name to tensor, that you can run. So I can run it for my name. And I have to use all caps because our input data is all caps, and I didn't do anything about capitals. So just use capitals. And if you run that, you'll get a whole bunch of zeros and ones every now and then. So our so the first 30, this first 41 characters, which is up to here. So that's our first letter, and that's our one hot factor. So it's, let's see if we go back up. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So J is index 12. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you can see that in position 12, we have the 1 because this corresponds to a J. And then the next, sorry, then the next one is 1, which is corresponds to the A, etc. So that is my name, my name as a one hot factor. Yours will be look slightly different. And if your name has a letter that was not in the alphabet that I used, then it's going to protest. So yeah, did everybody get their name as a tensor? Yeah, okay. So now we're going to apply that function as we just created. So we have our name to tensor, and we're going to do that for all the names in our name sample space. So I'm going to create a torch tensor that contains only zeros, and I'm going to make that um, the number of names we have in our sample times 15 times 41. So I had 8,800 names and I kept 90%. So that's around 8,000 names. So I have 8,000 names and each name consists of 15 times, well, then letters was 14. So 15 times 41 was 600 something numbers like this one here. And then I go through all the names and so I'll go for all of my input, which is the zeros, and I add the one hot factor. So now our input is a really massive array that has 8,000 by 600 something elements. And that's going to be the input for our machine learning algorithm. And then I do something similar for the output. So we want to do supervised learning. So we need to label our data somehow. And we know from the data set that some names are female and some names are male. So that's what this function does. It creates again zeros for the number of names and just one element. So that means that we get one output per name, male or female. And it's going to be number between 0 and 1. And I'm going to make 1 correspond to female. So that's what this does. It goes through all the names. If the name, if the sex of that name is female, I'm going to say the output is 1, and otherwise it will remain 0. So our output is going to be, oh, I should run it. Don't forget to run it. Run it. So if you look at the output, it's a whole bunch of 0 and 1s, where 0 corresponds to females and 0 to males. And then we get to our model. Oh, looks like I accidentally already put the solutions in there, which is maybe good because we're running out of time. So yeah, it's the same as before. So we have our init function and we have our forward function. This time I call it classification model. Doesn't matter what you name it, you can name it anything you want. And it depends on the module again. So all the functions are available from Torch. So here's the initialization function. And I create one linear layer that takes 600 something to 15, and then from 15 to 1. So what I have here is I have 2 hidden layers. I go from my inputs, I go to 15, and then from 15 I go to 1. So yeah, I use multiple layers, and if I use multiple layers, that really helps with the machine learning, and that made my model a lot better. So then I have the actual connection of the layers. So I say I take my x, which is the input, I put it through the first linear layer. So it goes from 641, I think, to 15. And then I take my next layer. So I take the output of this one and I put it into the next layer. So then it goes from 15, and then from 15 to 1. So the output of the second linear layer is just a single value. And then I put that in the sigmoid function that I mentioned before. So when you do binary classification, sigmoid is the best one to use. So that's I take the output of the second layer and I put that in what's called the activation layer, the sigmoid function, and I get another value y, and then I return that. So I execute this, and then I scroll down. We don't need this one because that was just for filling it in. And here is our criterion. So if we go back to the slides, where are my slides? This thing, we had our last function was the binary cross entropy, which is a horribly complicated function that I won't go in right now, but that's the one we want to use. So binary cross entropy loss instead of what we used before, which was a mean square error. But this is still the same. So the stochastic gradient descent, you have your model parameters and you have your learning rate. So we execute that as well. So now we have our model and we have our criterion and we have our optimizer. And now it's time to train. So I'm going to use 12,000 epochs. And I'm just going to start that right now because it takes a bit. Mhm. Anyway, while it's running, oh, there we go. That's the first epoch. So while it's running, this is also the same as before. So we have the model and we take our input. But our input is now not just one value, it's 641 values per entry. And I do that 8,000 for all 8,000 names. So our input was, if you remember, it was 8,000 by 641 elements. So that goes into our model and we get a prediction. And then we have our criterion, which is going to give us how close the prediction is to the output that we want. And that's this one, the binary cross entropy. So that gives us a number. Then we do the zero grad function because we always have to do that. We have to reset it to 0. The calculation for the gradients we have to set to 0. Then we calculate the gradients. So that's this backward step. So it goes from the output all the way back to the input and calculates the gradients along the way. Oh, I see a question. Actually, I see two questions. Can you please give some context on high learning rate and low learning rate? I assume 0.01 is low. What is high? Yeah, what is high? High is, well, too high is when your model just doesn't converge at all. So you can see the loss here. That should be decreasing. And if your learning rate is too high, it will actually increase again because it's overshooting its target. So if you see that, then it's too high, and then you want to make it lower. So it's a very subjective number. And then another question, do the loss values mean anything interpretable? Um, sort of, not really for our purposes. So for the mean square error, it was easier because it was an indication of how far off your predictions are from what your desired output is. So the best loss would be a loss of 0, but you'll never reach that because there's always some noise or some things that your model cannot understand. So really all you want to know is, does it still keep going down? And you can see here between epoch 11,000 and epoch 12,000, the difference is in like the third digit. So it's becoming really, really negligible. So yeah, then if you are at this stage and the star disappeared, that means your model has been trained. And I'm guessing for some people it might still be training. Um, is it still training for people? Oh, okay. Bye, Caroline. Coraline. Yeah, okay. Some people have completed the models. Okay, done. Okay, good. So the next one is you can find out what does your model think of your name. So put in your name in the put in your name instead of the dots, and then run the function. And the value I get is for me 0.27. Oh, I see a question actually. Sorry. If the same names appears as both male and female, how would this be handled in the code? Or we just need to read that out in advance? Yeah, so if name appears like Alex, for instance, can be both male and female. And if it appears twice in a data set, then the algorithm tries to teach itself that the name is male, but it also tries to teach itself that the name is female. Um, so that already means that you can never have a loss of zero because both cannot be true. But it's going to try its best. So in that case, it's just going to say 50-50, that this name is male or female. And that's the best you can get. So you don't need to read it out. Your model will just take it as it is and just try to minimize it.
Yeah,
Yep,
when this number that the code is returning us, if it is close to zero, it means that he think it is a male name. Am
correct.
I
Yeah,
right?
yeah,
Okay.
you're getting ahead of me. Yeah, so I have a 27, which is smaller than zero point 0.5. So the model thinks that my name is probably male. And the closer to zero point 0.5 this value is, the less certain it is that my name is male. So if I try the name of my wife, like Emily, it is 84% sure that my wife's name is female, and my wife is indeed female, so that is correct. Yeah, so it won't always get the name. For probably some of you, I see that somebody tried Alex. It got 0.19. Yeah, so that means that it thinks the name is male. So I got actually a higher number, and that's because there is a bit of randomness involved in training our data. So yeah, it's not perfect. Yeah, I see somebody else got 0.41. It is the same always every time I run it. It's just when I train the data, train the model, there's a big of element of randomness to it. And that comes from this thing here. So the stochastic gradient descent. So it's taking a very random path to get to the final answer. And also when you do the first input, the model is totally untrained, so all the numbers are random anyway. Yeah, I see that somebody says Aditya has a male name shooting 0.92. So yeah, it's very much not a foolproof model. And because we want to test our model, that's going to be the next step here. So we can test the model by using our test data. And that was the test data. That was the 10% that we chose not to include. So if we go all the way back to the top, almost all the way, for names, and this is the name test. So those are all the names that were not included in the training data. And we will use those, so name test, we'll use those to test our model. So that's what we do here. So we create a new column in our pandas data frame, and we're going to apply a function that says put in an f if the prediction is larger than 0.5, and otherwise put in an M, so male. Let's put that in. So here we have our test data set. Here we have the sex from our input data set. And this is what our model predicts. So this one's right, wrong, right, wrong, right. So it's not too bad. So then we count the number that are correct. So correct is when the pred column is the same as the sex column. So the prediction column is the same as the sex column. And then we divide the number of correct ones by the total names in our data set. So if we run that, we get our algorithm is 71% correct. Sorry, no, our model is correct 71% of the time. So it's really bad. I see here NCNA is generally an indicator of female name, so probably fooled the model a bit. Yeah, so when we put in the names, we padded everything with spaces at the end. So our model doesn't really know what the end is. And we have 3 minutes left, so I probably cannot go around to that. But if you scroll back up to the function name to tensor, so the second one I have, it inverts the name. So I changed it to 15 minus the length. So now it puts in the name. Sorry, now it puts in the padding in the front. So if I run this function and I do my name to a tensor, it's all 0, 0, 0, 0, 0, and my letters are actually at the end. So that means that my model is now going to look at the end of the name ending. And it's going to focus more on the name ending, which is probably going to give a better result. So I was meaning for that to be an exercise for you, but we ran out of time. I'll leave this cluster up for the rest of the day. I'll shut it down at 4. So in the meantime, you can just play with it. I'll also send you the code together with the slides probably tomorrow. And the recording will be published on our website. I think I still have some slides left. Yeah, so that's how to pick the layers and number of the nodes. I talked about that already a bit. So trial and error, intuition that you get after a while. And one of the biggest one is finding similar use cases. So if you type in your favorite search engine, model for this, and then you find something that looks like it, then you can start with that and then start tweaking it to fit your use case. Then the GPU acceleration, I didn't talk about that because it wasn't necessary for our data and model. But I have an example called CUDA.py, which I'll send out as well. And it will tell you how to transform the code into something that can be used for the GPU. So essentially, it's adding these 4 lines, and then your model can be used on a GPU. And it will be a lot faster if your model is large. And then further resources. So the PyTorch website has a lot of good tutorials that you can find. And there was actually a YouTube series that I found really good. You might want to play it at 1.5 speed because that person talked a bit slow, but it's still pretty good. And then, of course, there's me. So if you need any assistance, like with Compute Canada or Sascape, or if you want to get your program to work better, or you want to install servers, or you get virtual machines, or whatever, you can contact me. You can open a ticket in TopDesk, or you can just email me directly. And I think that is the end. Yeah. Okay. And we've reached exactly noon, so that is the end. Does anybody have any questions still? You're welcome, Frank. Yeah, it's a lot of take in. It's like a tiny sliver of what machine learning is, and we use the simplest of the simplest layer, but from here you can make it as complicated as you want.
Thank you very much for the nice talk again, Jan. I don't have any more questions. I already made a lot of them.
Thank you, Amintor. Okay, great. And thank you everybody for joining me. And yeah, good luck. And if you have any questions about this or you get stuck somewhere, don't hesitate to contact me and I'll help you. Okay, bye all.